So it's tough giving a lecture to a machine. Back when people gave lectures in real life, it was pretty easy to figure out how people were doing by walking in and getting the mood of the room, but you can't really do that these days. The mood of this room's fine. It's just one person in here, and he's been recording videos for hours now. But let me guess. So if you're at this video already, then I guess they're moving along, they're rolling. Or I mean, it's like you're watching this video like during the midterm. But in either case, that means it's time to do some things that'll unsettle people. So we have to talk about some stuff. What I like about the beginning of first-year courses in university is that everybody takes a few weeks to settle into figuring out what it is that this instructor's up to and how much authority they really have. And it's weird and sort of scary sometimes to think that I can say stuff and people just believe it. I hope that scientists and engineers don't do that. We shouldn't just believe everything we hear. But I mean, I could tell you stuff like 2 plus 2 equals 5. And you would probably not buy that. I'm working on it. We'll figure that out. But, okay, so what can I convince you of? I think I'm going to try and convince you of this. And you're going to hate me for it because you would rather believe that 2 plus 2 equals 5. I want to convince you of this. Int plus int equals int. That's it. That's all I want to tell. I want to convince you that 0 plus 0 equals 0. That should be an easy task. And by the time that we're done talking about this, you're going to wish that 2 plus 2 equaled 5, because it turns out that this is a pretty easy thing. It's a law of the universe. But if you forget about it, and it's surprisingly easy to forget about, then you end up with an error in your code. But before we can talk about that, let's talk about errors that show up in code. So here are some errors that I can think of. There are sort of two kinds, and you might even break it down further. The first kind of error you can end up with is a syntax error. So the word syntax refers to the structure of the language. So I have a C program over here, and you can see I'm doing some arithmetic, and I can compile the code and run it. But if I make a mistake and I say something that doesn't make any sense, so I write something like int c, and then I forget a semicolon, and then I save the file. If I try to compile the code, the compiler gives me an error. And the error is basically, I have no idea what you wrote, it doesn't make any sense. This isn't C code. That's a syntax error. And when you have a syntax error, the code doesn't compile. There's no question of what the code does because the code doesn't compile. So I'm going to undo that. So that's a syntax error. And when we talk about errors in code, it's a bit of a tough one because not every error is equal. There's a syntax error, which means your code is done. It's over with. There are certain laws that you can't break in C. And this is one of the laws of the universe, the law of gravity. You're not allowed to break this. When you have a syntax error, your code is done. But there are other kinds of errors too, just like how there are other kinds of laws in society. So there are laws of the universe. You cannot break the law of gravity. There are also laws like the speed limit. If you drive in your car, there is a law that says you have to go a certain speed or less. You cannot break the speed limit. Now you can tell me, is it possible to break the speed limit? Now this isn't advice. Talk to a lawyer first, but yes, it is actually possible. Your car likely can go faster than the speed limit. Now, my car is a different story, but there are laws that can be broken, and the same is true in C. There are also laws that are mostly like rules of society, and we've been learning a lot about those recently. Rules like walk down the one-way aisle in the grocery store in the right direction. And what we've learned is that not only is it not illegal to do that, if you break the speed limit, you could get a ticket. If you walk down the aisle in the wrong direction, sometimes nobody does anything. And there are also laws like common courtesy. So, for example, if you see somebody carrying a heavy stack of books, maybe hold the door open for them so they don't have to open it. Or, carrying groceries or whatever. I'm thinking a lot about grocery shopping these days. The same is true of C code. We know that there are laws that simply it is impossible to break. You can't break the law of gravity. You cannot compile code if it has a syntax error. If your code has a compile error, the program doesn't run. And accordingly, if you hand in code on an assignment that has a compile error, we can't mark it. It gets a 0. On the other hand, if you hand in code that does compile but doesn't work properly, well, that's still an error, right? The code isn't working as expected. So typically we call that situation a semantic error. So that's a case where you did write something that was valid C code, but it didn't do the thing you expected. We also sometimes call that a logic error. So the compiler took the code you wrote and accepted it, but maybe it didn't do what you wanted. And this typically can break down in one of two ways. One, you just wrote the wrong thing. The code is completely valid, it just does the wrong task. And that happens all the time, no big deal. I have that problem all the time. That's usually where you have to do the good old-fashioned debugging. You have to look at each line of your code, trace through it by hand if necessary, until you figure out where the problem was. But there's also this other issue, and we'll see this later in the course. It's hard to produce this now. But there are some things in C that are sort of like the speed limit. Things you really shouldn't do. It's considered to be a very bad idea to do them. But there are times in life when it's okay to break the speed limit. Now again, talk to your own lawyer. I'm not saying it's a good idea, but there are cases, for example, if there's a forest fire and you have to get out of town and the road is empty, I'm sure somebody can forgive you for going a bit over. I don't know, I'm not a lawyer. The same is true in C. One of the reasons we have to learn C in this course is that it gives you absolute control. We saw in previous videos, the compiler will sometimes see us doing the wrong thing. It'll say, oh, you're printing that as an int when it's actually a float. But all it does is warn us. It's saying you might be breaking the speed limit. So an example would be this situation here. So as we saw in the previous video or in a previous video, who knows what order you're watching these things in, you get these compiler warnings if the compiler spots that you're doing something that you really shouldn't be doing, but you're still allowed to do it. And that's an example of breaking the speed limit. If you do that, bad stuff could happen, but you're taking responsibility. It's now your problem as the programmer. Generally, though, we need to avoid that. And certainly anything the compiler is warning us about, we shouldn't be doing in CSC 111. If you go on in higher level courses to do very low level programming, like programming of embedded systems, like the microcontroller inside a dishwasher or something, you will see cases where actually it's quite justified to do the equivalent of breaking the speed limit in the metaphor, not in real life. But those are examples of, if they're accidental, semantic errors or logic errors. And what I want to talk about today is how to do arithmetic. And I want to convince you that 0 plus 0 equals 0, I guess, or int plus int equals int. And we'll work our way up from there to the 2 plus 2 equals 5 thing. But it's worth considering that when you have errors in your code, they can come in two flavors. The syntax error, of course, is the most obvious one. If the compiler says the code doesn't work, then you're done. But there's also this, where you write code, it looks good, the compiler takes it, and then it doesn't do what you expect it to. Maybe it never finishes running, it just keeps running forever. We'll see that example next week. And maybe also it runs and finishes, but the numbers it prints out are incorrect. So we're going to talk about that now. I'm going to hydrate. Because you could hear me clear my throat a minute ago, I needed some hydration. It's very refreshing. All right, so I'm printing out the values of A, B, and C. I guess we'll clear all these errors off the screen. So I compile this. I save the file. Thanks to the compiler, I guess I caught that one early. I save the file, I compile it, and I run it. And before I run it, let's make sure we know what's going on. We'll try tracing through it. So I'm going to start tracing here. I create a variable A. It's an int. It has the value 6. On the next line, I create a variable B. I draw the box properly. I create a variable B. It's got the value 10. And on line 13, I compute the result of this assignment statement. And we should know by now the rules for assignment statements. We ignore the left-hand side, and we only worry about the right-hand side until there is a final number there. Okay, so what's the value of B? Well, it looks like currently, okay, let's draw our B's correctly. Currently, the value of B is 10. So what's 10 over 5? Well, 10 divided by 5 is 2. So what I'm doing is I am setting C to be equal to 2. So I make a new variable C, because this is a line that contains a declaration and an initialization. Its name is C, its value is int, and its numerical value is 2. Its type is int. Okay, so, and then I should expect, if I run this program, it prints out A is 6, B is 10, and C is 2. And there it is. Good. Okay, so all's good so far. But the question is, if I uncomment these lines that I have down here, what's going to happen? And before I run it, let's just see if we can figure this out. And the idea is, this is an example where having diagrams and working things out on the side on paper is really helpful, because our human brains want to do something with this that the computer does not. So here's what happens. If I take a look at that first assignment statement, I'm just going to highlight it. That's this one here, B times A over B, and I assign that to X. So what's B times A over B? B times A, and then I put that in brackets just to be clear, divided by B. Well, it looks to me like what I'm doing is I'm saying 10 times 6, so that's, I'll sub in the variables first. So 10 times 6, all divided by 6. And we stare at this for a minute and say, well, this is obvious. All divided by 10. I guess it's not that obvious. So 10 times 6, all divided by 10. And we look at that and say, okay, so obviously 10 times 6 over 10 is just going to be 6 again. Okay, let's take a look at the second assignment statement. Okay, so the second assignment statement is b times a divided by b. Okay, well that translates to 10 times, and then I've got 6 divided by 10. And if I think of this mathematically, what I'm doing is 10 times 6 over 10, well that just equals 6, right? So let's try uncommenting that code. We'll save the file for safety, and we'll run it. And so the point I want to make is, if we just look at this and we glance it over and do it in our heads, it looks like x and y should have exactly the same values. I'm just noticing now that my print statement didn't have x and y in it. That was embarrassing. Good thing I caught that. That would be an example of a semantic error, because the compiler will let me forget to put x and y at the end, as we've seen in a previous video. So I compile this and I run it. And remember that from what we can tell, it looks as if 10 times 6 over 10 and 10 times 6 over 10 should of course both equal 6. But they don't. So x is 6, well that looks good, but y is 0. So what's going on? I mean, does 1 plus 1 equal 2? Or does 2 plus 2 equal 5? That's a tough one. So let's change examples. All right, so here's a little bit of a simplified case. I've got A, B, and C again, and this time I just do A is 6, B is 10, and C equals B over A. So we'll draw this out and then see what we think. There's A, it's 6. There's B, it's 10. And then we create a box for C, and we give it a value. And we'll even draw out the assignment statement, even though it seems like overkill here. C equals B over A. Okay, so, well, let's do the right-hand side first. What's B? It's 10. What's A? It's 6. So what's 10 over 6? Okay, so it turns out that 10 over 6 is 1.666. Okay, and then I store that into C. And you might already notice a problem with this. So C is an int. Am I allowed to store 1.666 in an int? Well, no. But we know already that if we try and store a real number into an int, all we do is chop off everything after the decimal point. Okay, so I store the value 1 into C. Well, that's too bad, but it's my fault for choosing an int instead of a float for that variable, right? Well, let's try running it and see what we think. So I'll save the file, and then this is called arithmetic2.c. The value of C is 1. Okay, all good so far. And you might say, well, that's no good. The value of C should be 10 over 6, or 1.666. But it makes sense because I chose the type int for my variable C. So what happens if I fix it and I choose the type float instead? Because you think to yourself, well, of course, a float can contain the value 1.666. So we'll save the file, and we'll run it again. Oh, I guess I better remember to print the value of C as a float with %f instead of %d. Well, this sounds like fun, so I'll do this, run it, and it's still 1. I get the wonderful gratuitous decimal expansion of a bunch of zeros, but it's still 1. So what's going on? I thought 10 over 6 is 1.666. And here's a problem. So a lot of programmers notice this weird issue where the decimal expansion just evaporates, and they figure out a way of fixing it, and they become superstitious. So here's what somebody who just experiments with it might discover. I think to myself, wow, all those ints and floats mixed together. Maybe I'll just use float because I know that floats can be real numbers. Okay, so I save the file, I compile it, and I run it, and sure enough, 1.666. So it's not like C doesn't know how to deal with division. It obviously can do it. But what happened? Why is it that when A and B are ints and not floats, the value comes out to be just 1 instead of 1.6. And this is a place where we can experiment and figure out what's going on and find a solution. But this is a place where it's good to be a bit more theoretical. Because if we're not careful, we are going to get superstitious. A lot of programmers notice this and they stop using ints forever. They can never use an int again because ints don't behave the way they expect them to. and we can't have that. We need ints. And so now's a good time to maybe, I don't know, pull back a bit and talk about things theoretically. So the issue we have here is that int plus int equals int. And I've got some examples that I can draw all over. I've got a better program to draw on too. So here we have this, some basic examples with multiple types. And the key thing to understand here is that the rules of assignment statements are actually responsible for this problem. So every variable in C has a type. I guess we figured that out already because when we go through our diagrams, we draw a name and a type for every variable. So let's do that for this example. So here's A, and it's an int. Here's B, and it's also an int. And then I've got this value called G, which is also a float. Now you might notice there's sort of a convention forming here, which is that if you have int values, I swear I just can't draw the letter G. If you have int values, often we name them I or J. If you have float values, we often name them F or G. We don't have to though. We are obviously allowed to name int my int or something. We can actually use variable names that are as long as we need them to be. We can even include underscores in our variable names. The notes talk about this a bit. We do discover that in very small programs, we often like to use one-letter variable names to prove a point because it's easy to talk about them. In assignments and things, you'll see that we like to use nice long variable names that are descriptive because as our programs get bigger, it's good to have descriptive variable names because the programs become self-explanatory. If all of my variables are called X, Y, and Z, I've got no idea what they really mean. So let's see, we'll just get rid of that. Oh, whoops, I guess I was drawing my diagram the wrong way. I'm going to redraw this. And if we're lucky, I might even edit it out of the video, the part where I screw up and have to redraw it. If we're unlucky, you're going to be watching me talk to you about how I should have edited the video. B equals 4, and then G equals 2.0, and it is a float. I'm already enjoying the much smoother drawing I get in this different program. So I have these variables, they each have types, but here is something that may not be obvious. It's not just every variable that has a type. Every time any number is used for anything, anywhere in the program, that must have a type. So every variable has a type, but more generally, every value in the program has a type. And that means that it's not just true that A, well, if I use the name A in the program, I'm talking about an int. But if I write an expression like A plus B or A plus B times G, this has a type and this whole thing also has a type. And we need to learn how all the different types interact. So I'll just get rid of that. And if we don't, we end up encountering that problem we saw earlier, where even though we store the result in a float, for some reason we lose the decimal expansion. And so we have to talk about if I perform operations on values, what type comes out. And the rule that I like to think about, the one that I like to meditate on a bit in this part of the course, is int plus int equals int. The type that comes out of an operation is determined by the types that go in. So if I take two ints and I add them together, then the result is going to be an int. If, on the other hand, I take two variables of type float and I add them together, then predictably the result is going to be a float. The problem is, what happens if I mix things together? So what's the result of adding an int to a float? And this is a tough one. But the language has a very well-defined rule for this, which is if you have two different types and you're mixing them together with an operation, so you're adding an int to a float or a float to an int, then what we do is keep the type that retains the most information. If we take int plus float and we turn it into an int, we're going to lose what's after the decimal point. But because we have a float in there, I guess we might want what's after the decimal point. So instead it makes sense to lose less information. Int plus float equals float. And the key here is that if int plus int equals int, and this applies to any other operation too, so int times int equals int, float times float equals float, int times float equals float, but also if I say something like int over int, that equals int. The type of what comes out is based only on the types of what go in, not necessarily based on what makes sense with the values that I'm working with. The language doesn't care what value comes out. The type that comes out is determined only by the types of what go in. So int over int equals int, float over float equals float, int over float equals float. And we'll see also that if I write something like double plus float, we've already seen that the double type gives us more precision than float. So it's no surprise that if we want to lose the least information, we want to keep double. So double plus float equals double, double plus int equals double, and so on. So I'm going to trash this. So then the question is, how do we evaluate complicated expressions? And the answer is we have to, as we work through arithmetic expressions, keep track of not only the numbers, but also the types. So I want to do this assignment down here. Okay, so int z equals a times g over b with some brackets. So we know already this is an assignment statement. So I'm going to make a box for z because I'm eventually going to need it. Okay, so int z. But then I'm going to ignore this. We've already seen the first rule of assignment statements is ignore the left-hand side until you have only a number on the right. And it's important so that we don't get confused about statements like x equals x plus 1, because of course that looks ridiculous, but also because types can be confusing too. If we look at the left-hand side of that assignment, we might get distracted by the fact that the type of z is int. That has nothing to do with this. Until we have a final number on the right-hand side, we're not allowed to look at the left. Okay, so let's work through the right-hand side of the assignment statement. So we know because of the way brackets work, we should do a times g first. Okay, so I'm going to compute the number as the first thing. So what's a? A is 6, based on my diagram. What's g? G is 2.0. Okay, so those are the numbers. I want to compute 6 times 2.0. But at the same time, I better work on what the types are. So what's a? The type of a is int, and the type of g is float. So I'm computing int times float, 6 times 2.0. Okay, so what's 6 times 2.0? 6 times 2.0 is, well, I guess 12. Okay, fair enough. What is int times float? Well, int times float equals float. So the type of this value that comes out of the brackets is the float 12. Often the way I would draw that is I deliberately put a decimal point in anything that's a float, even if it's just 0.0. So what I'm computing now is 12.0, the float, divided by b. I'll even write the word float above it. Okay, so what's the value of b? Well, let's see. So b has the value 4, and that is an int. So now I'm computing float divided by int, and that would be that would be a float. So float over int equals float. I keep the type with the most information, and 12 divided by 4 equals 3. Okay, so we might see that we actually have to do two types of algebra here, one on the numbers and one on the types. And if we don't, we can get ourselves into trouble, especially when division is involved. Although to be clear, the problem still exists even if we don't do division. It's just more subtle, and there will be exam questions that test it both with division involved and without. There are also cases where certain operations only work on certain types of data. So if we don't know what the type of something is, we have no way of actually performing the operation or knowing if the operation is possible. But in any case, I now have reduced the entire assignment down to int. I can now bring back the left-hand side. Int z equals 3.0 because I know that the number that comes out is a float. So int z equals 3.0. I then take that 3.0 and I store it in z. But wait, z's an int, which means I can only store the integer part of the expression. Okay, now if it turned out that z was being set to 3.5, the only thing that ends up in the variable is the number 3. Because z, whether or not I'm trying to assign a decimal point, the integer variable can only contain the integer part of the number. So that's one expression. Let's try another one. Just like before, in this case, I'm going to start by setting up a diagram. And I generally recommend that if we're tracing through code from top to bottom, it's a good idea as we go through it to cross out the lines that we're done with. So as I do this line here, I create a variable called a, and I set it to 6. And then I get rid of this. Now you think that's sort of, like, why would I need to do that? The answer is because what if later in the program when a has some other value, I don't know, like this, I'm somewhere down here, If I ask you, what's the value of A? You might get distracted and go up here and say, oh yeah, A equals 6, because you see this assignment statement. But A doesn't equal 6. A now equals whatever this is. And so it's good to sort of cross out lines as you get to them so you don't get distracted and end up using a line that no longer applies. Because remember that just because I set A to 6 doesn't mean A is always going to be equal to 6. Okay, so then I've got int B is equal to 4. And then, just like before, I've got a float called G, and it's equal to 2.0. And then I get down to this assignment just like I had before. So I've got a value Z. It is an int, and its value is, well, I guess I have to do this assignment. So before I do the assignment, I better cross out that left-hand side. I do not want to be unduly influenced by what's going on the left. Until I have a final number on the right, I shouldn't pay any attention to the left-hand side. So I'll work through this. So I guess I should have followed my earlier example and crossed these out properly. Everything's different over the internet. In person with chalk, this is dead easy. So A over B. So I've got 6 over 4, and I'll just cross those out. And then up here, I should keep track of the types. So I've got int, and I've got int. So 6 over 4. Well, in real numbers, 6 over 4 is 3 over 2, which is 1.5. But I'm not working in real numbers. Int over int. What is int over int? Int over int equals int. The type of the result depends only on the types of the operands. I know it seems weird that why would it be int if we know that it could come out to be a fractional number? And the answer is the compiler is looking at this and the language has said, we don't want to do any more work than the programmer asked for. It takes the processor more work to do division of real numbers than division of integers, with the result being an integer. And unless you are using a float, the programming language doesn't assume that you need a fractional part. And as a result, if you take int over int, the result will always be an int. If you want the result to be a float, make one of the operands a float. Do float over int or float over float. So int over int equals int. And that means that 6 over 4 cannot have a decimal expansion in this context. So 6 over 4 is 1. Okay, so then I've got the integer 1 times g. Okay, so what's g? In this case, I'm going to actually write that over here. So 1 times g. Okay, well, obviously, this is just going to come out to have the same value as g. So g is 2.0. So the value I get will be 2.0. And the type, I have an int here, and I have a float here. Int times float equals float. So what I end up with is writing int. The final assignment, once I bring back the left-hand side, is int z equals 2.0. I'm realizing now using z isn't great if I'm also using the number 2. Int z equals 2.0, and just like before, I only store the integer part of the value. If that came out to 2.3, it would still go in as only 2, and I'm getting self-conscious about my number 2s here. Let's draw a nice loopy-looking number 2. Here we go. Z now contains the value 2. And you might notice that it turns out that any type issue that happens, so this is not the right answer. If you think about A times G over B, so that would be 12 over 4 is 3.0. But in real numbers, 6 over 4 times 2 should be 3.0. It should be the same thing. These two expressions in real numbers are the same. And yet in C, they come out looking different. Here, the answer is what we expect, 3.0. But here it's 2. The issue isn't the type of Z. The issue is the type of the operands and the order that I'm doing them. And that's one of the reasons we have to care so much about the way types interact. So let's go on and try another one. And I'll set up my diagram. I won't obnoxiously cross off parts of the text because that didn't seem to work very well a minute ago. So A equals 3, and then I've got B, and it's an int as well, and it equals 4. And here I have C this time, and it is a float for the time being equal to 2.0. And just like before, I want to set up a variable z, and you might notice this time z is a float. And the point I'm trying to prove here is often if we notice that we're missing decimal places, we want to make the variable at the end a float. But in some cases, the problem is happening long before we get to that variable. So let's do the assignment. I'm going to cross off the left-hand side for my own safety, especially the z, and then we'll go through it. So A is equal to, at this point, 3. B is equal to, at this point, 4, and then that would mean that a plus b is apparently 7. And then, of course, in the type realm, that's int plus int, which equals int. So now I have int divided by float. So I've got the value of c here is 2.0. So 7 divided by 2.0, I think predictably is 3.5, because int over float equals float, and 7 divided by 2.0 is actually 3.5. So I store the value 3.5 in the variable z. So here, coincidentally, everything sort of worked out the way I expected it to, which is nice. And of course, if I really care about that 3.5 that I had at the end, it's pretty important that my variable z was a float. So let's try a variation on the same thing. Here you'll notice I've transposed some of the types. The type of z is still float, but the types up here are a little bit different. Okay, so a is an int. This time b is a float, and c is an int. And I guess I shouldn't have, that's a bit of a typo. So this is 2, this is 4.0, and this is 3. Okay, so a plus, and then just like before, I'm going to cross off this. We'll make a box for z for when we need, actually, maybe I'll make that box over here. All right, so let's run through it. So the value of a right now is 3, and the value of b right now is 4.0. And we can see that a is an int and b is a float. So int plus float, well, the result of int plus float will be a float, and the result, and this will be 7.0. And then the value of c at the moment is 2, and c is an int. So what I have is, I'll draw that up here, c is an int. So what I have is float over int. And that means that the result that I end up with is a float. And here, 7 over 2 is 3.5, just like before. And then I take that 3.5 and I store it in my floating point variable z. So let's try another variation. Int z equals, so it's the same variation as the previous slide with only one change, and that is this. The result variable has a different type. And this is actually sort of the flipped version of that problem that we saw earlier. So I'll set up my diagram again. Maybe I should draw boxes better. That's a really ugly box. One has to have standards in life. Mine are low but increasing. So then there's c, and then this is an int, this is a float, and this is an int. And a is 3, b is 4, c is 2. But I'll put 4.0 to make it clear that b is actually storing a float. And then I make a box for z for when I need it. And it's an int this time, and let's run it through. So the value of a is currently 3, and the value of b is currently 4.0, and that would be just like before, int plus float. And int plus float equals float. And this equals 7.0. And then c is 2, and the type of c is int. And I've got float over int, which is still float. And I've got 7.0 over 2, which just like in the previous couple of examples has been 3.5. And so then I take 3.5 and I store it in z. But remember that even though I have a 3.5 over here, the mixture on the right-hand side between int and float still gave me a floating point result. Z is an int. But only at the very end do I care about that. So the reason we always ignore the left-hand side of our assignment statement is that it's only when we get this final number down here that we begin worrying about what to do with the type of z. So here, now that we have a final number, we figure out how to put this number into z. So z is an int, which means we have to store this just as the integer 3. That's all there is to it. But if z had been a float or z had been some other type, we do not care under any circumstances until after we've done the calculation. It doesn't affect what we do in the meantime. And that's why if we go back over to this issue that we had earlier, where we thought So if we go back to the version that I was working on before I got superstitious, where I had int a and int b, and my argument is it's fine for a and b to be ints because they contain integer values. I shouldn't become afraid of using ints because of weird issues like this. And even if I do become afraid of using ints, I should still learn about the difference because I'm going to have to be asked exam questions that'll require me to know the difference. So there's two paths to choose. I prefer you choose the path where you're not afraid of it and do still understand how to do the exam question. But I guess if you want to be afraid of it, that's still fine. Just be able to do those exam questions anyway. So if we get to this point here, and I clear that, and I try compiling and running this, we can see that in my initial version where I had this as an int, the obvious solution that we saw at first might have been, well, hey, of course the value is going to come out as an int. So I'll clear it again. We'll start from scratch. So I cleared it too many times. So the value of c is 1. So 10 over 6 is supposed to be 1.66, and the value of c just is 1. And we look at that and we say, well, of course it's going to be 1. C doesn't have the ability to store a decimal expansion. And that's true. We do need c to be a float here. So we change that. And this is the natural thing most people can figure out. It's that next step that causes trouble. And that's one reason why having a diagram and keeping track of types can be helpful. So we run this. Now the value of c is 1.0. So what happened? Well, what happened is when we went to evaluate the assignment statement, c equals b over a, and I guess I should make a diagram here. So there's a, it's 6. There's b, it's 10. And then down here is my eventual value of c, which will be a float. A is an int and b is an int. So c equals b over a. So what do I do here? Well, if we get too wrapped up in the idea that the type of C is float, we might not notice the problem, which is that the programming language could care less what the type of C is. Its job right now is to do the right-hand side. It will not look at the left-hand side until it's completely done everything on the right. So let's work through the right-hand side only. Let's ignore the left and just work through the right. Okay, so what's B? Well, the value of B is 10, and the value of A is 6. And that would be int over int. So I take 10 over 6, which is 1.6, but it comes out as just 1 because int over int equals int. And then I take the 1 and I put it in C. And so the issue here is that we know that a floating point value is needed, but we need to have the floating point value exist somewhere before we do that division. So while we're on this subject, what are our options? So the obvious option would be we could just change the type of one of these operands to be float, because then we'd have float over int. We could change both of them, but we could just change one of them. And that gives us what we want. But what if I told you couldn't do that? So what if it were a contrived exercise where I said you can't change the type of A or B? So that could happen. I mean, you get all sorts of ridiculous exam questions in university courses, right? But it also could be that you're writing code in a context where you can't change the type of the variable because you need it to be an int. Maybe you're using A and B for other things, and they need to be ints because you need to use them as ints elsewhere. So what do? What if you have no options? A and B are required to be ints. So you have a few solutions. Now, the ones I like the most are actually the less official ones. The less official ones are leveraging what we just learned to make one of the operands to the divide operator a float without changing the types of variables. We could also explicitly convert one of the operands. And I'm going to talk about the former solution first. So we remember that we know that int over int equals int. But we also know that int over float and float over int, that's supposed to be a comma, those equal float. So all I have to do if I'm computing b over a is come up with some excuse to make either the numerator or the denominator a float. And I think about this for a minute, and what I could do is I could say something like this. b times 1.0. Anytime in C that you put a decimal point on something, even if it's a numerical constant, that value will be of type double. And therefore, this is b times a float, or a double, and that means that the result will be a float. So we have float over int. And so we'll try this. You can see here it works. This results in this bit of the expression actually being turned into a float before the division happens. So I end up in the float over int case. I could also try something else, like I could write b plus 0.0. That's a floating point number. It's a pretty boring one, but it's a floating point number. And that means that I have int plus float, which equals float. So then I end up on the outside with float over int. And so we can try that and make sure that that works too. And the symmetric case also applies, so I'll just back this up. It shouldn't surprise you that I could also do the same thing in the denominator. A times 1.0 will be a float, because every time I put a decimal point in a number, the language will assume that I want a float. It doesn't care that I put a 0 afterwards. It sees the decimal point and believes that what I need is a floating point value. And as I said, by default, it actually does, the type of this isn't float, but actually double. But it's still fine, because we know that we can convert a double to a float or a float to a double. We just have to worry about losing that precision. But if we're working in float, it's okay to mix in a double every now and then. And we still get what we want. I really like this solution. I love it. I think that, and a lot of students can come up with this on their own, and they can come up with this even during an exam if you know the rules for types. But you might look at this and say, this looks a little bit like a hack. I mean, it doesn't seem like a proper solution to this. So we have one more option that, although I view for the purposes of this course, the thing I just discussed to be perfectly valid. You would not lose any marks for writing it that way. 0.0 plus a, or a times 1.0. Those are great solutions. I love those. There is this way that the language gives you that's the proper way of doing it. And it's an operation called a typecast, which we often just say cast for short, which is to say to the language, yes, yes, I know, this is an int, a is an int. I want you to force it to become a float before going further. And the way you do that is you put the name of the type you want in brackets before the variable. So this little sub-expression here, a goes in as an int, but this bit converts the value of a to a float before going any further. And that means that we now have int over float happening here. And you can see 1.66 just like before. And we could do the same thing up on the top with b. Usually it's better to use brackets to make sure that it happens before the division operator and not after. And of course the usual order of operations applies. Brackets come first, then multiplication, division, and then after that addition and subtraction. So we've seen this problem of having to work through the algebra of not just the numbers but the types. We've also had our introduction to this issue with int over int equals int, which is a general problem called integer division, and it shows up in every language. People in other programming courses right now are struggling with it too. We've seen it early, and because C is so consistent, once we learn how to handle types and it becomes second nature to us, it'll become a lot less of an issue. And so going forward, we'll notice that there are a lot more things we can do with values than just addition, multiplication, subtraction, and division. But the rules still apply. The type of what comes out is determined based only on the types of what go in.